Science Institute, and I'll be your host for this session. So our Learning Science Institute has been conducting research as a part of the Humanities and Social Science Research Program, supported by the National Research Foundation of Korea since September 2023. This project focuses on establishing a learning science ecosystem for public education. So today marks the first seminar, 2025, hosted by the Learning Science Institute on the public education learning data. And before we begin, the presentation materials are available here through the QR code on the screen. So if you need the seminar slides, please feature and then have the presentation. Hold on. One second. Okay, now let's go further to introduce today's distinguished speaker, Dr. John Stamper. Dr. John Stamper is an associate professor at the Human-Computer Interaction Institute at Carnegie Mellon University. He is also technical director of the Pittsburgh Science of Learning Center Data. His primary areas of research include educational data mining and then intelligent tutor systems. As technical director, John oversees the Data, which is the largest open data repository of international education data for researchers in the learning sciences. John received his PhD in information technology from the University of North Carolina at Charlotte. Prior to returning to academia, John spent over 10 years in the software industry, including working in several startups. Okay, so today Dr. Stamper will present on continuous improvement of education technology through discoveries with AI and data. In his presentation, we'll discuss how big data, AI, and machine learning can enhance the efficiency of education system, especially through the adaptive learning technologies. And after the presentation, we will have a 10-minute Q&A session. Okay, so without further ado, please join me and welcome Dr. John Stamper.
So, my research background is in computer science, but I really got excited about doing educational work while I was doing my PhD, and really got into excited about this idea of adaptive learning and intelligent tutoring. And again, this is almost 15 years ago now, so what I found interesting is that the results from these intelligent tutoring systems are so much better than traditional educational technologies, yet it's not ubiquitous. And really the reason why is they're really hard to make, and it takes a long time to make them. So I really started thinking about how could we make that process of creating adaptive learning easier, and came up with the idea about using data and using data to generate the artifacts. And so, first a question for you. Let's assume a student is working on a particular skill, and they get the first question right, the second wrong, the third right, the fourth wrong, the next two right. Who thinks the student knows the skill at this point? And who thinks they'll get the next attempt correct? Who thinks the student knows the skill? Who thinks they'll get the next one right? All right. It really depends, right? This is what we call knowledge tracing, though. So knowledge tracing is where we can track what the student knows, and really there's just two ways the student could know this, right? The student already knew the skill prior to this opportunity, or at this nth or existing opportunity, they actually transition from the unlearned to the learned state. So those are kind of the two ways, and this knowledge tracing really is a big foundation of much of my work. But even though if the student knows the skill, it doesn't necessarily mean that it's correct, right? Because they could know the skill and get it wrong, and we call that a slip. Or they could not know the skill, and they might get it right, particularly a multiple choice question, right? Where they just get a correct yes. So why do we even care, and what does this knowledge tracing allow us to do? Well, one thing it allows us to do is track the learning over time. And so this is what we call a learning curve. How many of you are familiar with learning curves? New people? Okay. So this is the error rate on the y-axis and the opportunities for students to apply a particular skill. So this is a group of students working through a particular educational data technology, like imagine they're doing questions in their learning management system. And we can see the error rate declining. Sometimes you'll see learning curves where it's actually the correctness rate, and probably that would be a better way, but I'm a computer scientist, I like to reduce error. Some people like to see students get better over time, but here we go. And this looks like a pretty good learning curve. Students start out, knowing about 60% on that first opportunity, and it starts going down, and we'd like to see this go down. With adaptive learning, we might have students dropping out, right, mastering. So students might be mastering as they're going on down the line, so it may not be as pronounced at the end. And we may never get to a zero error where every student knows every skill. But this allows us to assess, right? At any point in time, we can assess and see where the students are. We can also apply some sort of model of prediction, and that's what this blue line represents, where we can then predict the next opportunity. So we can do what I asked you to do at the very beginning, and have some quantitative methods to say, yeah, we think the student's going to get the next one right, or we think the next student's going to master this skill in X number of opportunities. So yeah, and we can use this data to assess the students, and also then we can use it to drive adaptive instruction. So if we know the skills that they know and don't know, we can use that to give them the next best problem to help them learn. And this comes to Data Shop. Has anyone ever used Data Shop here? I see a couple of people. Okay, nice. So Data Shop is something I started way back in 2006 timeframe, right when actually before I came to CMU. And the idea was to collect educational data. And originally it was mostly coming from people doing research studies in the classroom. So, often we would have data sets around 30 students to 100 students. But as time has gone on, with the MOOC phenomenon and online courses, we started collecting larger and larger data sets, and all different kinds of domains as well. And now I believe this is the largest open repository of educational technology data from interactive technology systems. And Data Shop allows us to do a bunch of things. First of all, it allows for full data management, so you can upload a data set, and anyone can upload a data set to Data Shop. You just have to sign up and agree to our terms of use, which says you won't provide any identifying information. And you can have access control then of who gets to see the data. You can share it with your colleagues. You can make it open to the public. You can attach files to it. So if you have other, you want to have a pre-test and post-test that was paper written, people will attach that sometimes. Other times people will attach analysis. You can attach papers that you write about a data set, and that's a great way to get citations, is having your paper attached to your data set at Data Shop. And it's been really great for secondary analyses, and there have been several thousand papers that have used Data Shop data sets in the Educational Data Mining Conference, Learning Analytics Conference, and AI in Education. So how much does it have? Here's a picture from, I think, December. Yeah, I didn't get a chance to update this, but roughly we have almost 5,000 data sets right now, representing almost 400 million student actions and over 1 million students. And I always like this number. This is 1,300,000 hours of students sitting in front of a computer that we have. So lots of data, and you can see a whole lot of different domains as well. Initially we started having a lot of math, and we still do have a lot of math. And folks like Carnegie Learning and What I said, hopefully it didn't say the computer was shutting down or something. Partners like Carnegie Learning and our own cognitive tutor authoring tools that did a lot of math work. But more recently, our biggest providers have been the online university providers like our Open Learning Initiative and other types of MOOCs. But yeah, everything from math to chemistry to English to Java programming, lots of languages. I don't think we have any Korean language data sets, but if you guys are welcome to get data in. We do have some Chinese and others. So yeah, lots of data. And in DataShop, we use this term knowledge component. Has anyone heard that term? So knowledge component, I use it interchangeably with skill. KCs or knowledge component are really knowledge that can be tracked in the data. We originally thought about using the term skill, but a lot of educational psychologists and other folks got kind of pushed back, like what you're tracking really isn't a skill. So we kind of made this own term knowledge component, which has become really popular in a lot of the educational data science communities. And then you'll also hear the term knowledge component model. And really all that is a mapping from the skills or knowledge components to the individual problems. So we have this model then that maps every opportunity, which opportunities are generally problems that students have where we can get a correctness input. And really these mappings represent hypothesis of what we think the student's learning looks like. And so a good model should create a good learning curve. And we use learning curves as an empirical basis to tell us that we have a good model. So if we see this declining error rate, or if it was the other way and we saw the students getting more correct, we would assume that the model is doing what we want it to do and teaching the students those skills. So it should be give us accurate predictions on transfer, students learning, and as we know, repeated practice on the same task, if it's modeled correctly with the same skill, we should see students making progress and the error rating going down on those skills. We should get a declining error learning curve. Something like this. Again, this is another one from a geometry area data set. You know, we're seeing kind of this downward trend. There's a little blip. So, and this is an aggregation of all the knowledge or skill, knowledge components or skill in this data set. So number one here represents a data point for every student for every skill. And that's their second opportunity from every student on every skill. And you go down and go down. And again, we might expect this to be a little lower at the end, but this particular is an adaptive system. So along the way, students are also mastering and dropping out of the curve. We can drill down. So as I said, that was all the knowledge components. Well, here's some of the lower level ones from that same curve. And we can see that this gets a little more choppy, and that's because we got less data on these curves. And we also start seeing some kind of interesting things. You know, some like circle area still have this downward, and trapezoid area sort of, again, still have that downward slope. And that blue line is that fitted model. So that kind of shows us the direction. What about square area here? You know, probably where that big blip is out at the end is a point where we only have 1 or 2 students left in this. The rest have mastered it. Mostly what this shows me and what rectangular areas show me, students really know that skill coming in. We're giving them way too many opportunities to apply square area. We're really wasting their time. And it turns out that in the tutor, students have to find the square area to move forward on more difficult skills as well. But it might be better in those cases to just give the student the answer to the square area because we're kind of wasting their time doing it again. But other ones, particularly like that composed by addition up there in the third one, that doesn't look like learning's occurring at all. So we can drill down and take a look at this one. And I can say, why is this opportunity number 4 so much harder than opportunity 3? And we can drill down and look at the problems that students are getting at that opportunity. Similarly, why at 11 is it so much harder than 12? And so this skill composed by addition is where students are finding the area of a composite shape. So imagine finding the area of the side of a house where it's composed of a square and a triangle. And it turns out that in some of these problems where they're having these error rates that are going down very fast, the problems are saying, find the area of the side of the house. It's composed of a square and a triangle. And these other ones are just saying, find the area of the side of the house. So what we deducted from this is that there's a hidden skill here where students have to decompose some of those problems, the composite shapes. Some of them, it tells them what the composite shapes are. Others, the student has to realize there's two shapes there and they have to find both of those areas. So what we were able to do is on the existing data set, put this new skill or hypothesized skills in there, which this decomposition skills, we call them. And then we fit the data back to our model and we got a better learning curve. In this case, we were using AIC and BIC, which is a Kachi information criterion and Bayesian information criterion. Those are just, if you're not familiar with those are both just two methods to compare models to each other. Lower, in both cases, lower numbers are better. And this was the textbook. We got lower fit or lower values, meaning we got a better fit with this new model that had additional knowledge components or skills. And so this, and this was on old data. So it should even be more a stronger indicator because the original model was what was being used to drive the system. So this new one should really provide an improvement. And so we actually, to see if that's true, we did an experiment where we created new version of the cognitive tutor for algebra, geometry in Carnegie Learning's cognitive tutor. And to do this, we had to add the new skills in. And then we had to create some new tasks where we would isolate that particular skill. So we created some problems where we were asking students to, tell us what shapes or what equations they would use to solve those composite problems. And then, of course, you have to change the instructional message, feedback, and hints as well. All this is, it's a little bit intensive, but it turns out it was very worthwhile. We ran an experiment, and this was kind of the original where students in the control didn't really get that much opportunity to apply the composite shapes and had a lot of problem on the composite shapes, which is the blue. And in our treatment model, they got much more practice on these composite ones, which were the harder skills. And we did show significant learning increase overall. And students were, maybe more importantly, students were able to master it in 25% less time. So imagine if we did this for every system, we might be able to shave off a whole year of high school. So again, this is very similar to other things that have been shown in intelligent tutoring. So this learning can really, really be accelerated if you have a good model. All right, so that was one example where we really did what we called this hand search machine test version, where we found it by our humans found the little blips in the curve, and then we used the model values to kind of narrow down and fix it. But can we do it completely at scale? And the answer is yes. And what we need to do is provide some sort of machine learning. So we need to turn those models into something that the machine can read. And so we take something like this, and imagine these are some problems that students are doing in an algebra course or a math course. And you can see what we do is we create what we call a question matrix, which is just a matrix of whether a particular skill is assigned to these problems. So you can see this first one just has multiplication. The second one has multiplication and subtraction. This is really a toy example, but this one has multiplication, subtraction. So these two should be alike. But do you guys see any other skills that we might be missing in these problems? Like, are these two really the same? Right? This one is harder, probably, right? Would you say that's harder? Why is that harder? negative number. So negative number might be someone, how about this one? Yeah, order of operations. So we might have some other hypothesized skills that aren't in here. And again, this is kind of a toy example, but what we could do then is having this matrix, we could see whether these skills matter in this type of learning. So, and it may be the case that really addition and subtraction are really the same skill in this order. By the time students get to high school, we hope that addition and subtraction, like they know both of them, right? So it should be a common skill. So those might merge into arithmetic or something. And we can try that. We can try merging all these, and we can try splitting on them. And we need some sort of model. And here's we use what's called AFM, or additive factors model, which is just a linear regression, whether the student will get it right or wrong, and has these coefficients for the skill and the learning rate of the skill and the number of opportunities. And that's really what we fit that blue line in the data shop as well. This is the model we use. And then we can take one of those Q matrix and try it out. We send it to the supercomputer, processes what the fit is. And then we can try merging the skills or splitting on the skills and try all these different ways and do, several 100,000 or even up to 1 million different combinations of these models and test it against. And this is what we did. And this is the root mean squared error in this one of the original kind of the human driven model and the machine learned model. In this case, lower is better. And this is the learning slope. So this is kind of the slope of those curves. And in this case, you would want a higher slope is better. And you can see, and I think all but one of these, the LFA or learning factors analysis is what we call that process, did better and found better models. And so, again, this isn't perfect, but other people had done this before we did it, but they did it with kind of only untagged skills, so just numerical ones. Because we have these hypothesized tags or the skill names on there, it should make it easy to interpret the results if you're merging two things. And it doesn't always work great. Sometimes the hardest skills merge together in this process. So for that geometry area, sometimes if you run it, you can get like fine trapezoid area and fine circle area could merge together because they're both very hard skills in that one. But you can see that pretty easy when you have incorrect merges in there, because we can follow the track of the skills. We can find models that fit better. And in theory, that should be driving better at driving the instruction, should be more optimized. We should be able to get students through the material with less number of problems. And again, because we have these skills labeled going in, we're going to come back with human interpretable labels on the outside, so we can make sense of them. All right. I showed that really toy example, right, with different math things, but it gets a little harder when we're talking about things like a business course or a history course. How do we figure out these skills? And it actually isn't an easy thing, even for expert instructors to do, right? We have this expert blind spot. Sometimes we're not sure of what skills it is. We're trying to figure out how, when we identify that kind of that peak in a learning curve where it looks like something's wrong, something's harder, how can we find out what's wrong? And we've been doing a lot of crowdsourcing work or learner sourcing. And we've also been using AI, which I'll talk about as well. Here's an example of our learner sourcing work. And if you're not familiar, how many of you know what crowdsourcing is, right? Yeah, crowdsourcing, you have people on the web. Learner sourcing is when we use students to do those kind of things, and we should be doing a crowdsourcing task that has educational value. This work was kind of pioneered by Yoo-Ho Kim, who's at KAIST, and we use a lot of his underlying theory based on how we're doing some of these. But here are some questions, two different questions where we might ask the students, what do you need to use? Here's a Python one. To solve this, what are 3 skills you might use to solve this problem? Here's a similar one for chemistry. Name 3 skills you might use. We also did some things where we had we took those problems where there was this blip, right, where one was harder than the next one, and we said, why are these, if this is a problem here at the top and here's another one, this one's finding the area of a swimming pool where you have to subtract, and here's the one where you're finding the area of a wall and with a door and you have to subtract. And it turns out this one's harder, maybe not because of a skill issue, because of a drawing issue, but we would ask the students, why do you think question 2 might be more difficult than question 1? And then basically we would analyze these and see if we could find an additional skill involved. Well, in straight out crowdsourcing, it was really bad. Students were really bad, and only 14% of the crowd that we used out of 120 students, only 17 were able to match 2 of the 3 skills that we identified in the problems that we had. Students also struggled as well. Turns out students are not very good at just looking at something and hypothesizing the skills. So this was also not great. So then we turned to some AI methods like LDA and MFS, our modeling techniques. Yeah, again, this did not have much success using topic modeling with NLP techniques as well. So then we turned to large language models. And this is work with my colleague, Tom Mitchell, at the machine learning department at Carnegie Mellon. And our students, my student, Stephen Moore, and his student, Ramesh Mucker, got together. And we were trying to see, can we use large language models to help support this? And in this case, we ran it on 2 subjects that we had a lot of data for. One was an e-learning course that we have, and one was a chemistry course. It turns out, not unexpectedly, that the model did a little better in chemistry. So the large language model has a pretty good knowledge of chemistry. E-learning, which is kind of a more nuanced type of learning, right? It's not as well known as chemistry in the large language model. It only got a 35% match. So again, we're still not doing very good on any of these with finding these models. Yeah, so I think the key takeaway on this is generating these knowledge components is hard, but these automated techniques that we're doing are showing some promise, and it's very important. You know, a really good model can really save a lot of time in student learning. So, all right, so we have that idea of students need opportunities to learn, right, in those learning curve graphs. Well, often I get asked, how many opportunities do we need for any particular skill? Does anyone have an idea? Well, for a learning curve, I always say I need 2 to make a line and 3 to make a curve. So at the very least, that would kind of be the minimum. You'd probably like to have 3. If I have 2, I can at least show a direction. But again, it's probably a bit more nuanced around the domain and the algorithms. Generally, I think most domains are going to need probably 5 opportunities for any particular skill to show the learning correctly and give students a chance to learn. Well, it turns out, you know, particularly in college level courses, we really don't usually have 5 opportunities. College professors are notoriously bad at generating lots of problems in their courses. So the more opportunities you have, the better. Yeah, we actually did a study. This is with TutorGen, which is a startup that I did, and Harvard with their Harvard X platform. And we found in most of their MOOCs, and particularly the MOOC that we were doing on astronomy, they really only had 25% of the total opportunities or questions that were needed to correctly trace the knowledge and make the course adaptive. So we had experts in there get together and create it. And it took them about 200 extra hours to create the additional content. So as we're talking about opportunities, this kind of brings us to this question of fast and slow learners. So how many of you would say you're a fast learner? How many are slow learners? Yeah, a couple. Okay, it's all right. So anyway, I'm going to probably shock you here anyway. Yeah, so we actually had this idea, like what features or what attributes make people a fast learner and a slow learner? and can we identify those and then figure out like how to move slower learners to faster learners. So this article by my colleagues Ken Kadinger and Paulo Carvalho and others is really, it came out in 2023, and probably in the year of the LLM. This might be the most important paper in educational data science for sure. But the astonishing regularity, what they looked at is they took a bunch of data sets in DataShop, and they were looking to try to see, could they hypothesize a simulated student with learning features of fast learning and slow learning, and try to match it to the actual data sets in DataShop. And here's what they came up with. And this middle one is the knowledge components, and those are the skills. And we can see the skills all have different learning rates. So this is looking at where the students come in and where the students go out, where the skill is and where it is from the time they learn. And we can see a lot of these skills have different learning rates. And they created these simulated students that had different learning rates. But when they map the actual students, you get that top line. And it was astonishingly parallel. Students are all learning at the exact same rate. And that's really astonishing. Basically what that's saying is there are no fast learners or slow learners. Everyone is really, it's just about what you know coming in and how many opportunities you get. So this is pretty, okay, and they didn't just do it on, math. They did it on a bunch of different kind of broad data sets in college. And so these are 4 data sets, and you can see a little variety in this English grammar one. But yeah, they went ahead and applied it to a bunch of different ones, looking at math and science and languages. And yeah, there is some variation in a few of these data sets, but it is astonishingly regular. And this really tells us that, yes, there really isn't a thing of fast learners and slow learners, right? So this to me is super important and kind of drives home that need for opportunities, right? To be able to get people to catch up, really all we need to get them to do is actually do their homework and do those opportunities, more practice. They're currently running this on all the data sets in DataShop. So there will be a paper that has like 4,000 plus data sets. And it is, again, it is astonishingly regular how students are learning on the learning rate. So yeah, opportunities are important. So yeah, main takeaway, we need more opportunities. Yeah, and so this kind of leads to my next thing. How do we get more opportunities? Question generation. So we need a way to get more questions. And this goes back to the very early days of large language models, way back in 2018, when something called BERT came out. And we started noticing that BERT was really able to do some really cool stuff with language. And how could we use this to actually generate questions? And it was doing so with good English. Google came out with their T5 transformer, which was also quite good as well. And we could use these knowledge components or concept mappings that we have to inform creation of multiple choice questions and use it to test question quality. So we created this generation pipeline. I won't go too much into this, but basically using some BERT to do the question generation, and then we kind of ranked the list of how good the questions are by looking at the concepts in there. And yeah, we were able to generate lots and lots and lots of questions. Creating questions using these large language models, as you might guess, is pretty easy to do. It's the quality that is the important thing, right? Sometimes it generates questions that are not that great. And so we never want to show an instructor really bad questions, particularly wrong questions. As soon as we do that, they're probably not going to believe in the stuff we're doing. So what we wanted to do is rank the questions that were generated. From one course, we were able to generate something like 7,000 questions. A lot of them were kind of garbage, throwaway questions. So how do we get those down at the bottom and really get the high quality questions at the top? And we proposed some metrics called information score, a standardized information score, which took into account the length, and And then we also used getting all the way to 2020, 2021, where we had GPT-3. We used GPT-3 then to classify the models as whether it was useful or not useful. And yeah, we actually got the top level, and we could make a cutoff of like the top 10%. And they were generally really good questions, especially if we used all three scores to kind of rank them and list it. Was it perfect? No. Here's a confusion matrix. So the ones where the expert and the GPT classifier agreed are there on the diagonal, 36 and 99, and where they disagreed, still pretty high, 52 and 16. So still not great. So still looking for better ways that we can check the quality of these questions. But we did, yeah. So we created some metrics. And one thing we wanted to do is just throw this question out there with the matrix and kind of challenge the community. Can you find better matrix inside our work when you do it? But we know we need some good work that's being done. And we also realized we needed some data sets of questions that really had good quality questions in them that we could compare to. So that took us into the question evaluation. And my student, Stephen Moore, who graduated this past September, really led this work with crowdsourcing, using some things like the item writing flows work, and using some LLM methods. Now we're all the way up to GPT-4. Last year. So automated evaluation of MCQs, multiple choice questions. So if you see MCQ, that's multiple choice question. In NLP, there's already, in the natural language processing space, they have metrics like Blue, Meteor, and Rogue, which are really used in machine translation, but we figured we could apply those to some of the questions. Things like perplexity and grammatical errors, complexity and answerability were other metrics we found that were existing. Of course, there's human evaluation. The gold standard is just having humans tell whether it's a good question or not. We can use IRT methods. So item response theory can give us some quantitative data on that. But there is some subjectivity, and that kind of comes down to these rubrics. There's several rubrics out there, particularly for multiple choice questions, some for open-ended questions as well. One that we utilize is this IWF, or item writing flows rubric. And there's actually several item writing flows rubrics, but the one we used had 19 criteria in it, and you can look that one up. I think there's a 13 criteria one as well, but they have things like grammatical cues, convergent cues, logical cues. Here's 4 of the criteria in there, and here's a problem. What are the subatomic particles known as protons? And you can see the answers, and you can see in this case, item C is missing the period, which is kind of this grammatical cue. Convergent cue is the word subatomic is used in both A and C. And then logical cue, subatomic is also in the question. And implausible distractor, D is doesn't make any sense for the question. So these are some of the writing flaws that humans go through and can actually use these criteria for valuing the quality of questions. And so then we went back. Steven's my guy who does the learner sourcing and the crowdsourcing. Could we get crowdsourcers and students to start looking at this? And in this particular one, we use Prolific. I'm not familiar if you're familiar with the crowdsourcing platform Prolific, but it's a little better than some of the others like Amazon Turk, because you can actually, we were able to get people who had at least a bachelor's degree from the US, people who had, we even were able to get people who had chemistry degrees. So we were able to work down to a pretty good level of crowd workers. And wow, we were surprised that that did work using that item flow rubric and taking the majority case when we had a bunch of workers, we were able to find all the match that the crowd workers on average, matched the human evaluation for 100% of the calculus that we did and 98% of the chemistry. So pretty fantastic. Again, it was only on 3 questions. So it wasn't a huge amount of data that we had. But it was really good. However, and what's surprising to us, but it really wasn't scalable as it was taking, it cost us a lot of money to do this one because we were paying a lot more than typical crowdsourcing tasks because we were asking them to go through this 19-point rubric, and we kind of had to train them also on the rubric, which we paid them for. So yeah, it probably wasn't worth the effort, and it might just be better to get expert teachers to do it for the cost that we were spending. But it did show us that this could be, these rubrics, there was something to them. So then we were like, can we actually use some automated methods? So we created a rule-based method as well as a large language model-based method. And again, trying to use those to tie each of these 19 points in the rubric. And we compared it to the human evaluation. So we had 3,800 classifications done. And this was basically 200 multiple choice questions times that 19 items in the rubric. And here, maybe surprisingly as well, the rule-based methods did better than the large language model methods, but both did pretty well on a 1-to-1, so for each of the rules. But to get it to match all 19 for one question, it was much smaller. So 91% of the individual rules were correctly matched. But when we looked at an entire question of all 19 for one, only 15% in the rule-based and only 12% in the GPT-4. But note, if you have 2 humans do it as well, you'll often get mixed results on some of those as well. So this is pretty promising. And it does look like this automatic techniques are scalable methods. And again, interestingly enough, the rule-based method, which is kind of older AI techniques, actually did quite well. GPT-4 wasn't terrible. And so now we're looking at which ones did better on each of those individual rubrics. And if we combine it, can we create one model that does a lot better? And this is kind of leading us to this scalable automatic question usability evaluation toolkit, which is available on GitHub. Anyone can download it, anyone can use it to test the quality of multiple choice questions. And it really lets you go through, and it was quite successful. Using Socket, we improved the total, and this kind of combined both the rule-based and the LLM. We got 94 total accuracy and 38 of all the labels. So that's really quite good in this one. So my student, Stephen, who's now graduated, is still working on this in his postdoc, and we're hoping to see this really even continue to improve. Yeah, I'm gonna jump through this a little bit because I got a few more things and we're getting close to time. Yeah, I think a lot of these current metrics are failing to really get some of the deeper attributes that we want of whether a question is good or bad. And we still do need better methods for identifying what are good questions. This Socket, as we call it, toolkit, it does promise to offer some interpretability compared to a lot of the black box methods that other people are using. We do think as LLMs continue to improve, we'll see these methods start getting better accuracy. Yeah, I'm going to jump off to one real quick thing that I've been working on too is when we start wanting to test these models, we've been looking at how we can do fast experiment at scale in online courses, and we've been doing that with adaptive experiments. Basically, this goes back to Herb Simon, who, if you don't know Herb Simon, you should definitely look him up, but he was a Nobel Prize winner in economics at CMU, where he did some game theory stuff. But one of the founders of AI and one of the founders of AI in education, and one of the things he said to something close to this is every classroom is a laboratory, and that's what I look at too. So even if you're not running an experiment in your class, you sort of are. You're saying this this content that I'm giving the students is what I believe is the best content to get them to learn the material, or I hope you're saying that. But it's, you know, it is an opportunity every time you teach to run an experiment, because there's lots of different things you can try, right? And there are lots of things that people try. So every time you're in the classroom, consider it an opportunity to run an experiment. And I would say every course is just a simple series of experiment that you're running. So you have this opportunity to try a lot of different things. But we should formalize that, right? And so we created this framework that actually won, I guess it's now 2 years, back in May of 2023, we won the X Prize for the Digital Learning Challenge, which was about creating experimentation at scale really fast. And so this work kind of came out of that, where you have a traditional randomly controlled trial. We were looking at if we have a lot of different experimental conditions, can we narrow down to the best ones faster using some AI algorithms to do that? And yeah, so here's kind of a traditional, the top is a 50-50 experiment in the control and the treatment. And in the bottom here is a 37 allocation. And, you know, what we were saying is, as we're running the experiment, if we have a lot of different conditions, can we kind of throw out the conditions that aren't doing very well? We were doing some stuff with student self-reflection to see which kind of prompts got better student learning. So we had a whole bunch of different prompts, and we're trying different types. And yeah, this adaptive experiment would, like, as we would go through, we might start with a 50-50 split. And then as students are learning, the green condition here might get 67. And then the last one, it might give 83. And this really follows a lot of medical experiments is where we were using this from. We were pulling this these techniques from medicine, where, you know, you really want to give in medicine the best treatment you can, right? To a patient. And we thought, yeah, in education too, if we're testing things, we should try to get to the best learning for most of the students as we go on. And this, I'm not going to go through this in the interest of time, but we get kind of down to these normalized curves of where each condition is pretty quickly. And here's kind of an example of a traditional experiment with 3 conditions would look something like that. And then, you know, you go through and maybe after the experiment, just choose the blue one. The middle one is the best condition. Well, in an adaptive experiment, we might reach that by, you know, a lot more students getting that best condition before the end of the experiment. I'll do a few, do I have time? Yeah, got like 2 minutes. I'll go through, and I want to leave time for questions, but a few other projects that I'm working on. One project is called, we're working with a company called YIA Air Science, where we're in Uganda, and we're working with students on old style texting phones, and they actually listen to to a STEM course on the radio, and then they can build experiments at home, and they take quizzes via their old style USSD phones. And yeah, we're starting to see really actually good results. And this is really, you know, we are reaching the very, very last mile of students in Uganda with this. Sometimes there'll only be one phone in an entire village, and they'll be using this to create STEM stuff. A lot of my work, so most of the knowledge component and skill modeling stuff is what we call knowledge tracing. There's also something called model tracing, where we work on individual problems with hints and feedback. And this is work that goes way back to my dissertation work in 2006, where we are automatically generating hints and feedback. This work is really picking up again, as you might expect with the use of large language models. We're able to start really creating these interactive hints and feedback for students. And yeah, we're seeing how we can use this. We're integrating this with our open learning initiative, LMS at CMU as well. I have a project on doing what we call real-time knowledge sharing, where this is actually used with the Navy and Boeing and Google Cloud, where we're generating videos and trying to assess whether human-generated videos like YouTube-type videos are sufficient quality to send out to Navy sailors for training issues where they're not learning something on a aircraft carrier. For example, we've been working with the F-18 fighter community, which is on an aircraft carrier, and how we can quickly generate learning opportunities for people. Right now in the Navy, it takes them about 2 years to make a training video, and as you might expect. And again, some of that is for real reasons. Their manual is a standing order. So if you don't have one of those steps in the manual in a video, that's really considered breaking an order. So, a lot of the work we're doing in here is with sailor-generated videos or the learner-centered videos that they're generating. We have to make sure all those steps are in there. And right now we're doing that with some probability, and we still have to have someone validate it. So I guess some final takeaways, which hopefully you got. I think there's huge opportunities, right, for AI now, along with the rise in every other education has one space where we have lots of opportunities for AI. But I would say lots of people are coming in and using these LLMs to do a quick one-shot, no-shot kind of learning. And I would say, let's not throw away the 25 years of learning science research that has been done just for this shiny new LLM toy. And again, more and more, I'm worried about people using and relying just on the LLM with prompting and not doing anything with the data. Data is still, I think, as relevant as ever. And I feel like we're still not harnessing the power of the data. So yeah, with that, I'll take questions.
Okay, thank you so much. Applause. Okay, we're gonna have a short 10-minute Q&A sessions, and I love your picture. By the way.
Yeah, one of the things we do at CMU is for our master's ceremony of graduation in the School of Computer Science, they always give us lightsabers to march in with, and we march in with the Imperial March from Star Wars.
That's lovely. Okay, if you guys have any questions, please raise your hand, and our staff's gonna give you a mic.
Yes.
Oh, what a good mic. Really, thank you very much for your presentation. It was a really valuable opportunity to gain a better grasp of research utilizing data through various case studies. Actually, when I have some opportunity to need the assessment of teacher, I have previously received feedback from teachers. They expressed that, like athletes, they would benefit from real-time analysis and feedback on their teaching process to enhance their instructional effectiveness. You shared a lot of various case studies focused on students. Is there any case focused on teacher for data analysis? Yes, that is my question.
Yeah, there's there is a lot of work going on with how we can help the teachers, and we see a lot of like trying to figure out what these analytics or metrics could be, and that's some of the work that I do. And those learning curves could be done in real time nowadays, right? And we do have some dashboards in some of our systems for our online courses that we are able to show the instructors. I think one thing to take note is instructors they want dashboards, and they are very, very bad at interpreting the data on dashboards. So it turns out that instructors are not great at using them when you spend a lot of time and effort into creating them. So that's one thing I caution about. We have had some success. One project we have is called Lumilo. And this is actually an AR/VR project that we're doing, where we created these dashboards where the teacher in the classroom is wearing a headset, and they're able to look at any of the sidewalls and see kind of a board of metrics out there, and they can actually they can see the students working on their in their online system. So they're working on the educational technology, and it can put little question marks on students that are having trouble automatically, so the teacher can just look out and see who's having trouble. They can see the rate of how students are progressing overall by just looking at the side wall. They can see students who are not doing the work, and it has a little Z sleeping thing over their head. That's been pretty productive as well for teachers. We tried all different AR, VR techniques where we had them holding up their phone or holding up and it turned out the headsets in this case were the best because they felt like they could look at the classroom and see the stuff happening without the students noticing they were doing it. And that's been pretty successful. That's one area. Most of my, in general, the work for teachers that's really exciting me right now is helping the teachers create new opportunities and questions as well as new content. So we've been also looking at how we can get teachers involved in the process, especially with these online courses that are already, they're kind of given, but how can we get teachers to modify it and do it in such a way that they're improving it so we can kind of get this learner sourcing with the teacher community.
Thank you very much.
Any other questions in the upline? There's one question in the Zoom, so we're gonna. Okay, so we have two questions, and one of them is, I find it particularly hard to generate high quality questions with the LLMs for advanced third or fourth year college courses. Does Sequit provide promising performance in this context as well?
It does. Again, the socket tool is really evaluating the quality of the questions. It's still not creating the questions. So still a lot of work to be done on, I think, the question generation. We also have some trouble, especially with more esoteric kind of courses, such as the third or fourth year courses. But the socket tool can, if you create a method that generates lots of questions, it can bring out and pull out the best ones. And then the next question.
Yeah, next question is, I really enjoy your lecture. It seems like learner interest is also important and can be considered in adaptive learning. Do you have any plans to work in the direction of the adaptive to learner interest in the future?
Sure. Motivation, metacognitive skills are obviously very important, and especially these days with student attention not being that great. We do some work where we're trying to track these more metacognitive attributes and seeing how students are engaged. I'm doing a lot of work with help-seeking behaviors. So particularly with the LLMs as a feedback tool, we know that students are really bad at asking questions in the LLM. They don't know what to ask. So how can we scaffold this? How can we scaffold the questioning and help a student really narrow down how they're asking the question and what they're asking for? We're doing that right now in a study that we're calling pedagogical prompting. So how can we put pedagogically relevant kind of statements from the LLM to help them kind of plan? Is this a planning task? Are you really trying to plan on how you're going to solve the problem? Or do you have a specific error that you don't understand? One issue with that is we found if you just give students something that doesn't give them the answer, they're just going to go to GPT-4 and put in the question and get the answer. So there's a fine line between trying to get them to stay with the LLM in your system where they're having this conversation versus just going outside of your system to get the answer.
Thank you so much. Any other questions? Okay, if you don't have any other questions, I'm gonna wrap up this talk. So thank you so much, Dr. Stamper.
Thank you all.
Let's give another big applause for the first for sharing this insight.